Hi everybody, so we got our second last lecture now, getting there, so just hold on. So the section 7.1 is about fermenters where we don't add everything beforehand, specifically the substrate. So we'll see that some of the microbes don't like high substrate concentrations. So what we'll be doing here is to gradually add substrate to the fermenter. We do this only in order to keep the concentration of substrate in the fermenter low. And this is referred to as fed batch fermentation. So let's get on with it. So before we get to the coding approach to handling fed batch fermentation, it's very important to understand how substrate via this function influences the growth rate. Okay, so it's all about, growth rate, and maximizing growth rate is really crucial in optimizing production rates. So what we have here is the Monod term. You've seen this before. So this is really just at very low substrate concentrations where the Monod term, and let's draw a line. So this term, this is not going to work. This term operates in this regime. So very low, and we always have to have this term because this is really the term that stops the bug from working if there's no substrate. Remember, if there's no substrate, the bug can't work. Okay, so this is the Monod term. The new term that we have today is the substrate inhibition term, and it's this term. And this is really only as substrate concentration gets high, we start decreasing the mu function or the mu value. Okay, so this is the bug saying, if you put me into a higher concentration of glucose, I don't like living there, and you will find that I grow slower than what I can grow. So in a sense, this section is about targeting this maximum and understanding how to target this turning point that is close to the Umax value. So if we look at what we've done up to now, we've only looked at batch fermentation. Okay, now batch fermentation, you will remember we had the molar balance given by that equation, and it is in your notes. So effectively we've reduced this equation by saying dNi dt is equal to V times dCi dt, and that would have been equal to Ri times Cx times V. In a batch fermenter, the volume remains constant. So what happens was the volumes cancelled out. Okay, and we ended with something that looked like this, and this is really what we integrated. And one might think of this as a concentration balance, but it's crucial to understand that there is no such thing as a concentration balance. We only have mole balances, and when we start fiddling with changing the volume, you will see that a mole balance is very important, because let's draw it. What happens now is we want to keep the substrate concentration low. So we're not going to add all the glucose right up front. We're rather going to gradually add glucose to the system. So the bugs in here, they'll be eating the glucose, bringing down the concentration, and if the concentration gets too low, we basically now add a bit of syrup, a high concentration of glucose, so that we constantly give them glucose to feed on. Okay, very important is that this equation will not hold anymore. And the reason for that links to the volume not being constant anymore. So in the fed batch system, and remember, the volume will now increase. Okay, as time progresses, we add liquid, so the volume will increase. So what you got to see is that the volume will increase, it will change, and of course the concentration value, depending if it's a substrate or a product concentration, will also change. Okay, so now we've got both concentration and volume changing. Okay, and this gets messy. If we want to do concentration balances, remember there's no such a thing as a concentration balance. We do, however, have mole balances. So what we're going to do in our approach is to say stick to the moles. stick to the moles and work out the concentrations afterwards. So we are going to integrate with moles, and remember that as you attempt that first part of 7.1. So let's have a look now. If we now have a increase in volume, we got to change a few of our equations. Okay, let's have a look at the substrate equation. So remember the mole balance, and that was given straight away in, I think, chapter 5, is always considering the accumulation of moles. And this will change because of stuff that we feed. In the next section, we'll see that we actually can take stuff out of the fermenter as well. Then we have a continuous system. And of course, we have the reaction term that we had before. We can just quickly add, because in this system, there will be substrate, biomass, and product. So we can add the additional two equations. The NP dt, of course, will just be equal to Rp times Cx times V, similar for dnx dt, that will be equal to Rx times Cx times V. So what you see here is no addition of product and no addition of cells to the fermenter. The only thing that we add is, and we should write it on here, is a flow rate, and this flow rate, QF, feed flow rate, doesn't have to be constant. It can actually vary. Sometimes you'll see that it's good to vary, and it will contain a certain concentration, typically a fixed concentration of glucose. Don't confuse CSF with the initial. When we start up, we have an initial glucose concentration. These two are not the same thing. Okay, and then very importantly, we need to include one additional balance, and that will be the volume balance, because we can show, if the density doesn't change, that dV dt, and remember now for the first time it will be important to describe the volume change with time. So we can say dV dt is equal to, well, that's quite simple, it will just be equal to the volumetric flow rate of liquid. So the assumption is that we are working at constant density, and we now have we have four equations. We have the free mole balances, and then we have the fourth volume balance. So these four equations are the ones that we want to integrate. And as I said before, we're not going to be too concerned about concentrations for starters. We're going to work with moles, and only afterwards are we going to convert back to concentrations in order to draw our concentration versus time graphs. So let's just have a look, because you've got to do this on your own. This is the last section of the work. I'm not going to do it for you. I kind of give you the answers, and you then do the integrations yourself. So let's just have a look over here at the old way of doing batch reactors, and here's the new way of doing fed batch reactors. So you will remember ODE int really called upon the fermentation equation, and here we gave typically a initial concentration value. So we would have had a CX0 value and a CS0 value and a CP0 value. Okay, the fermentation equation was typically a function of concentration and time. Okay, so ODE int called upon the fermentation equation, and in the fermentation equation we basically had the reduced form of the mole balance, which was that concentration differential term that we fed to ODE int. And also in the fermentation equation we called upon the response function. So we calculated R, we got the R values from calling upon the response function. If we call upon the response function, we are effectively asking what is the concentration, what is the response function given a concentration dependency. So the response function was a concentration dependent function, and given the rates we then had the differential of concentrations. Okay, what's new now is that we're not going to work with concentrations at all. So this down here represents the fed batch system, and here we will rather start by defining a initial molar amounts. Okay, so very important, we'll have NX0, CX0, and CP0, and also, very importantly, we're going to not just have the free mole balances, but also the volume balance. So you have to give the initial volume as part of the initial value. Okay, so what we are now integrating, the fermentation equation, is now different than before because it will be a function of the molar amounts and time and not concentration. Okay, so please have a look. There's a difference between what we have here and what we have here. And really, that is because we are going to be integrating the Ni dt instead of the Ci dt, what we had over here. And we will also be integrating dV dt. So these are the four equations that I have just mentioned. Okay, in the fermentation equation, we will still call upon the response function. So we're still going to calculate R's, and we're still going to have the response function. Response function is always just a function of concentrations. Okay, so the response function basically remains exactly the same. And we call upon the response function to return the rates. And after we've returned the rates, we now fit it into the Ni dt equations. Okay, so please note you're going to do the coding yourself and you've got to sort it out yourself. I'm not going to supply you with an example, but try and understand the difference between how we handled the constant volume batch systems, where we were able to get away with just a concentration differential. Now we have to work with a true mole balance differential, which is actually much easier in solving the whole problem. So when you are successful in integrating molar amounts, you got to always understand what ODE int returns. ODE int will return we can call it an N matrix, because it will be at different corresponding time values. You'll have the molar amounts of substrate, cells, product, but very important, there will also be a volume column that is returned. Okay, so don't forget this volume column over here. Okay, it's now part of the differential equations because, as I said before, we had 3 differential equations and 1 volume equation, and this is really what corresponds to the 4 values that got returned. You got to understand that. Okay, so in the end, we are kind of always interested in plotting concentration profiles. That's what we do, concentration profiles against time, whatever they are. So if you want to convert the N matrix, so the integration is done, we now just want to basically do a step so that we can get back to our old concentration matrix, the one we always had returned from ODE int. So this will be CX and this will be CP. Okay, to do this, it's not that hard because you basically take the same elements, okay, and for each element in the row you will take, if you want the concentration, so I can write it down here. Remember, Ci is always just Ni divided by V. Okay, please note that V changes, so you've got a different V value as time progresses. You've got a different N value, and this calculation will give you the concentration. So it's basically this divided by this giving this, and this divided by volume giving this, and this divided by volume giving this. I've given you the code, so now you can just do the conversion where you convert the N matrix to a concentration matrix, and then you can go back to your old ways of plotting concentration versus time. So lastly, let's just get back to this function we had right at the start. Remember, you'll see in this example, we'll focus a lot on productivity. And if we want the productivity to be high, we want the volumetric production rate of lactic acid to be high. And this will mainly be manipulated by mu. Okay, So what you got to see here on my mu gauge, and this is very important, is there's two sides to, well, there's really an optimum in terms of mu. You don't want to go too low. If your substrate concentration is too low, you're going to have a poor mu, and that's exactly what we have over here. But then on the other hand, if your substrate concentration is too high, you feed a lot of substrate, it builds up in the fermenter, then you also end up with a mu that is too low. Okay, so we want our mu to be as high as possible. That will be over here, okay, and therefore it is a balance, or it's a tricky business in terms of knowing how we should add substrate to the system. So you'll see towards the end how if we manipulate QF, the feeding flow rate of substrate, we can really improve the productivity. I'm not going to give it all away here. You've got to do the calcs yourself. But basically, you got to just remember that Cx, or you can also say Nx, will increase with time. Okay, so your cells are always growing, they're getting more. And because of this function, you preferably want to adapt in terms of your QF. Your QF, you don't want it to be too high. If QF is too high, you go over to this side. If QF is too low, you go over to this side, and you'll see this in your calculations. Okay, so it's all about feeding the right amount at the right time, trying to operate at the optimum, and this is really the optimum substrate concentration in the fermenter. Okay, work through those examples, try and not just get the answers, but try and see and understand what I'm trying to show you with the example. Good luck, enjoy it, I hope you learned something.